Okay, recording this one, and this is the last kind of bonding I want to look at. We looked at metallic, we've just finished off with ionic, and now we're going to look at covalent bonding. Thank you. First warning, I shouldn't have to do that. You're year 11. Put your phone down. So we're going to look at covalent bonding and how it's different from the other two. It deals primarily, in fact exclusively, with non-metal atoms. So covalent bonding is the bonding that occurs between two or more non-metal atoms. Non-metals have high electronegativity. There's that word again. Electronegativity, the ability to hold on, okay? The ability to hold on and gain electrons. So when two nonmetals meet, they end up sharing the electrons in order to obtain 8 electrons in their outer shell. Now there are some exceptions to this. We won't go into that today. But basically here I've got, what have I got here? Looks like oxygen to me. Oxygen needs 2 to fill its outer shell, so it gains, they sort of share it between themselves, and then you end up forming a covalent bond where the electrons are joining those atoms together. They're joining the orbitals, those shells, and allowing for those electrons to buzz around both of those atoms. So it's getting 2 from one oxygen, 2 from the other, and they're both completing each other's shells. Now, because they're both highly electronegative, neither one is going to pull the electrons away from the other. They sort of hold hands, one pulling against the other, creating this really rigid bond. Quite a strong bond. It requires a lot of energy to break. Okay? So if you can imagine, they both want these electrons as much as the other one. Yes. That's why the bond is so strong, because both of them are holding onto the electrons. So, Craig, if you just stand up for a moment. You've got an electron, I've got an electron. We both want to fill our outer shells. You're going to grab that one. Okay? I'm going to grab that one and pull. Okay? So now we've got this strong bond forming between us because both want these electrons. We both are stuck. We're rigid in our ways. We're both going to be stuck in a pair spinning around. Okay, that's what a covalent molecule is.
They stay together.
Exactly.
Help each other out.
Exactly. They complete the orbitals, but they're still trying to pull each other's electrons away because they're highly electronegative.
What are some examples?
What are some examples? Well, oxygen is a classic example. Just get the camera right. That'll do it. So oxygen is a classic example. All the like chlorine gas, bromine gas, any non-metal compound. That's why non-metals exist in pairs all the time. And water, which we'll learn about, is also covalent. It involves the sharing of electrons. Yeah. But there's a bit of a difference between water sharing electrons and oxygen sharing electrons because the electronegativity is going to be different. And that'll lead us into what we're going to look at today. So, if there is no electronegative difference between the two atoms, hydrogen gas or chlorine gas, for example, if they're the same elements in that molecule, okay, the sharing of the electrons will be exactly equal. Because the strength is equal, the strength at which they pull each other is going to balance out. And we call that a non-polar bond. If it's the same element, it's a non-polar bond. There's no direction in which the electrons are being pulled towards, okay? Because they're just in the middle, because the strength on either side is the same. So there's no what we call a pole. When we talk about poles in chemistry and physics, we're talking about one end versus another end. So why am I explaining about non-polar bonds? Because we need to look at what a polar bond is. If there is a difference in the electronegativity, if there is two different elements on that bond, okay, the sharing of the electrons is going to be unequal. Because, for example, with hydrochloric acid, we've got hydrogen and chlorine. It's a covalent bond. They're sharing electrons, but chlorine is more electronegative than hydrogen, so it tends to pull the electrons more towards it than it is pulled for the hydrogen. So as a result, you get a slightly, very slightly negative end and a very slightly positive end. Because chlorine is pulling the electrons slightly towards it, the chlorine becomes slightly negative. And because hydrogen is slightly losing control of its electrons, it becomes a little bit positive. And we call those dipoles, okay? And we give them these little symbols, a delta plus or a little lowercase delta minus. It's lowercase delta. It just means little charge, slight little charge, eeny little charge, okay? Because the electrons are distributed unevenly. Chlorine's pulling most of it towards them. So, Craig, I don't want to use you again, but if you just indulge me for a second. If I am chlorine, I've, more strength. Craig is hydrogen, okay? Craig wants that electron, but I'm just going to pull them more towards me. I have more electrons near me. Craig's, we're still sharing, but I'm more negative because the electrons are towards my direction because I've got the more strength. Does that make sense? Okay? And he's slightly positive because the electrons are shifting away from him. That negativity is shifting away. Okay? We'll explore this in detail. But just get the idea that if they're the same element, it's non-polar because they're sharing the electrons evenly. If they're different elements, you automatically have a different electronegativity because you've got different number of protons in the nucleus. Then you're going to get a polar bond. If you share one pair of electrons, you have what's called a single bond. If you have two pairs of electrons being shared, you get a double bond, as is the case with oxygen. And if there are three being shared, which nitrogen can do, phosphorus can do, and carbon, because carbon can form 4 bonds. If there are 3, you get a triple bond. All right?
Is that what you were talking about with the aluminium? How it's like triple bonded, that's why it didn't react.
Aluminium lost 3 electrons, which means it actually had a full 3+ charge. It's different to this. We're looking at sharing electrons. We don't actually have charged species, so to speak. We have slightly positive negative ends, but they're not full charge. Aluminium has a full 3+ charge, and that's why it was bonding very hard to its other ions. But nitrogen and nitrogen share 3 electron pairs to complete each other's outer shell. So that's why nitrogen is double bonded. It's the reason why it's the most abundant gas in our atmosphere, is because it requires a lot of energy to break that double bond. Okay? We need lightning to actually break nitrogen up. Lightning, volcanoes, or forest fires are how we get nitrogen into the compounds that we use for our bodies. Other than that, there are bacteria that will do it with specified enzymes. Nitrogen is a hard thing to get at because the more bonds you have, the more energy it requires to separate. So in this case, with hydrogen, you've got 1 electron each, and then they both donate to complete that outer shell. Remember, the first shell has a maximum of 2. With oxygen, they both are donating 2 electrons to complete each other's outer shells, and that gives them a double bond. They're doubly bonded. Doubler. Okay. Now, the electrons that are used in the bonds are called bonding pairs. The electrons that are not used to form covalent bonds are what we call non-bonding or lone pairs of electrons. And you must always show lone pairs of electrons when we're drawing diagrams showing the covalent bonding. And I'll show you how to draw the diagrams later. But I want to get the terminology down pat. When you see the term lone pair or non-bonding pair, those are electrons that are not involved in the sharing. It's the bonding electrons that are involved in the sharing. So oxygen, yes, it's sharing 2 electrons, but it has 2 other pairs that aren't doing anything, just buzzing around. So, what do you need to do? Well, by the end of this lesson, I hope to teach you how to be able to draw electron dot or Lewis diagrams and the structural formulae of a range of covalent molecules. I'll get a sheet to you with that, on how to do that, but I want to do a bit of practice with you guys first before I put it in an official slide form. All right, I'm going to stop the video here, and then I'm going to go into some practice on the whiteboard. I will have more information in an electronic form if you're watching these, and the notes will be on DayMap, of course, anyway. Just find it easy to work under lights.